The fundamental theorem of calculus. We begin with some remarks on terminology and symbolism. Consider, for instance, the integral from 0 to 2 of the square root of 1 plus x squared dx. This integral is a number that tells us the area under the graph of y equals the square root of 1 plus x squared between x equals 0 and x equals 2. Let's have a look at the various parts of this symbol that represents the integral. First off, we have the integral sign. This is basically a stylized S standing for sum. The endpoints of the interval over which we're integrating are sometimes called the limits of integration. We have a lower limit and an upper limit of integration. The expression representing the function we're integrating is sometimes called the integrand. And finally, the mysterious dx that appears at the end is a gadget that's known as a differential. We'll have much more to say about differentials soon. But for now, you may have noticed that the dx plays very little role here. The dummy variable. The letter that represents the variable in the integrand is a dummy variable. We can replace it with any other symbol without changing anything. For instance, the integral from a to b of f of x dx is the same thing as the integral from a to b of f of s ds, or f of t dt, or f of y dy, or f of u du, or f of any letter we choose to use times the corresponding differential. In fact, we could even abbreviate further and simply write the integral from a to b of f. For instance, the integral from 0 to 2 of the square root of 1 plus x squared dx could also be written as the integral from 0 to 2 of the square root of 1 plus s squared ds, or the square root of 1 plus y squared dy. All of these represent exactly the same number. One important role that is played by the differential is to indicate the variable with respect to which the integration is being done. This is important if the integrand involves other parameters. For instance, in the integral from 0 to 1 of the square root of k squared plus r squared dr, the dr indicates that the integration is done with respect to the variable r, treating k as a constant, and so the resulting value will be a number that depends on k. In the integral from minus pi to pi of cosine of n times t dt, the dt indicates that the integration is done with respect to t, treating n as a constant, and the value of the integral will depend on the parameter n. In the integral from 0 to 1 of x to the pth power dx, the dx indicates that the integration is done with respect to the variable x, treating p as a constant, and the value of the integral will depend upon the parameter p. Average value. Suppose that f is continuous on the closed interval ab, and let little m denote the minimum value of f on that interval, and let capital M denote the maximum value on the interval. It follows then that the integral from a to b of f of x dx is between little m times b minus a and big M times b minus a. To see what's happening here, let's think of the integral as the area under the curve, and notice that little m times b minus a is the area of this small rectangle in the figure, and big M times b minus a is the area of this larger rectangle. It's clear that the area under the curve is somewhere between the areas of the two rectangles. Turns out that this is also true even when we're dealing with a function that's not necessarily non-negative. Now notice that another way to write this inequality is that little m is less than or equal to 1 over b minus a times the integral from a to b of f of x dx, and that's less than or equal to capital M. The quantity in the middle of this inequality is known as the average value of the function on the interval ab. So the average value of f on ab is the integral of f over ab divided by the width of the interval. Now the preceding inequality says that the average value of f is between the minimum value and the maximum value. Since we're assuming that f is continuous, the intermediate value theorem tells us that f must take on every value between its minimum and maximum values, and so it must take on its average value as well. This fact is the average value theorem, also known as the mean value theorem for integrals. It says that there exists a number c in the open interval ab such that f of c is equal to the average value of f over the interval. That is, the integral from a to b of f of x dx is equal to f of c times b minus a. Here's a picture to illustrate. The integral is the area under the curve. We can think of the average value as the height of the rectangle with width b minus a that has the same area as the area under the curve. And this theorem says that there exists a c strictly between a and b where f of c is equal to that average value. A function defined by integration. Suppose that f is continuous on an interval containing a, and let capital phi of x equal the integral from a to x of f of s ds. So notice here that the variable x appears as the upper limit of integration, so we use a different letter, here s, for the dummy variable of integration. For example, let f of x equal 1 over x and a equal to 1, then phi of x is equal to the integral from 1 to x of 1 over s ds. If x is between 0 and 1, notice that the integration is from right to left, and so we have a negative value for phi of x. If x is greater than 1, then the integration is from left to right, and so we have a positive value for phi of x. Now let's look at an animation that traces out the graph of phi of x as x goes from 0.25 to 4. Notice that once x is greater than 1, as we move from left to right, we accumulate more and more area, and so phi of x gets larger and larger. Here's another example. Suppose that f of x is equal to x and a is equal to 0. Then phi of x is the integral from 0 to x of s ds. Here's a graph of the function f of x equals x. Now here, notice that if x is less than 0, the integration from 0 to x is from right to left, but the function values there are negative, and so we actually will have a positive value for phi of x when x is negative. So now let's watch this plot of the graph of phi of x as x moves from left to right along the horizontal axis. Since the region bounded by the graph and the horizontal axis is always a triangle here, it's easy to write down a simple formula for phi of x. Notice that in the figure, the green triangle has width x and height x, and so its area is simply 1/2 of x times x, or 1/2 x squared. So the integral from 0 to x of s ds is equal to 1/2 x squared for all x. Now let's make a few observations here about phi. First, the function phi is continuous. Basically, this is about the fact that a small change in the value of x will cause a small change in the value of the integral that defines phi. 2. Phi of x is increasing when f of x is positive and decreasing when f of x is negative. When f of x is positive, phi of x is increasing because as x moves from left to right, we're accumulating positive area. When f of x is negative, phi of x is decreasing because as we move from left to right, we're accumulating more negative signed area. And third, phi of a is equal to 0 because the integral from a to a of any function is equal to 0, and the value of phi at the number b is equal to the integral from a to b of f of s ds. The derivative of phi. The definition of the derivative says that phi prime of x is equal to the limit as h goes to 0 of phi of x plus h minus phi of x divided by h. Now let's have a look at that difference quotient. This is equal to 1 over h times phi of x plus h, which is the integral from a to x plus h of f of s ds, minus phi of x, which is the integral from a to x of f of s ds. Now let's think about the difference between these integrals. Suppose the graph of f looks like this. The integral from a to x will be the area under the curve between a and x. The integral from a to x plus h is the area under the curve between a and x plus h. So the difference between those is simply the area between x and x plus h, or the integral from x to x plus h of f of s ds. Now we apply the average value theorem. The integral from x to x plus h of f of s ds is equal to some value of the function f of c, where c is between x and x plus h, times the width of that interval, which is h. So we have 1 over h times f of c times h, or f of c, where c is some number between x and x plus h. Therefore, phi prime of x, which is the limit as h goes to 0 of the difference quotient, is the limit as h goes to 0 of f of c, and since c is between x and x plus h, and f is continuous, that limit is simply f of x. So the derivative with respect to x of phi of x, that is, the derivative with respect to x of the integral from a to x of f of s ds, is equal to f of x for all x in any interval containing a on which f is continuous. So this tells us that any continuous function f is the derivative of some function. In particular, it's the derivative of phi of x. This is version 1 of the fundamental theorem of calculus. Now, since f of x is the derivative of phi of x, we also say that phi of x is an antiderivative of f. Some examples. Consider the function defined as the integral from 1 to x of 1 over s ds. Here s is the dummy variable, and the function depends upon x, and its derivative with respect to x is simply 1 over x, which is simply the function that we're integrating expressed in terms of x. The integral from 0 to x of the square root of 1 plus s to the fourth ds is a function of x, and its derivative with respect to x is just the square root of 1 plus x to the fourth. The integral from 0 to t of sine of x squared dx is a function of t. Notice here that x is the dummy variable of integration, so we can take the derivative with respect to t, and that turns out to be the sine of t squared. The integral from 0 to r of t squared over the square root of 1 plus t squared dt is a function of r, and its derivative with respect to r is just the integrand evaluated at r, that's r squared over the square root of 1 plus r squared. So notice that the process of taking derivatives of functions like these is really trivial. Now let's look at some variations on the theme. Suppose we have a function that's defined to be the integral from x to a of f of s ds as opposed to the integral from a to x. In other words, the variable appears as the lower limit of integration. How would we take its derivative? Well, it's a simple matter to simply reverse the limits of integration by introducing a minus sign. So we end up here with a derivative that's minus f of x. Now, what if we have something a little more complicated, where we have functions of x in each of the limits of integration, something like the integral from u of x to v of x of f of s ds? Well, the key here is to suppose that c is some fixed number between u of x and v of x, and break the integral up into the integral from c to v of x plus the integral from u of x to c. Here we're using the interval additivity property. Now in the second integral, we'll reverse the limits of integration by introducing a minus sign, and now the key is to realize that we're dealing with compositions of functions. The first term is the function phi composed with v of x. In the second term, we have minus phi composed with u of x, and so we need the chain rule to take these derivatives. The chain rule says that the first term is phi prime evaluated at v of x times v prime of x, and the second term is minus phi prime of u of x times u prime of x. And now since phi prime is just f, we have f of v of x times v prime of x minus f of u of x times u prime of x. Examples. First, consider the function q of x defined to be the integral from 0 to sine x of 1 minus s squared ds. Notice here that for any x, we're always integrating from 0 to some number that's between minus 1 and 1. Here's the graph of the function 1 minus x squared between minus 1 and 1. every value of this function q is a signed area underneath this curve between 0 and whatever value sine x has. Now let's look at an animation here that plots that signed area as x goes from 0 to 2 pi. As x goes from 0 to pi over 2, area increases. Then when x is between pi and 2 pi, we're integrating from right to left and getting a negative value. The derivative, q prime of x, that is, the rate of change in that signed area as a function of x, is the derivative with respect to x of the integral from 0 to sine x of 1 minus s squared ds, which we'll compute using the chain rule. The derivative of the outside function being the function capital phi of x, is 1 minus sine squared x. Notice we're simply substituting sine x into the integrand here. Then the chain rule tells us to multiply by the derivative of the inside function being sine x, and so we multiply by cosine x. Now 1 minus sine squared x is the same as cosine squared x, and so we have cosine squared x times cosine x, which equals cosine cubed x. Here's the second example. Let g of x equal the integral from x to x cubed of 1 over s ds. So here we have x in both limits of integration. Here's the graph of the function that we're integrating, 1 over x, and the region shaded in red here represents the integral from x to x cubed, where x is equal to 1/2. Notice that when x is between 0 and 1, x cubed is less than x, so we're actually integrating from right to left. When x is greater than 1, x cubed is greater than x, and so the integration is done from left to right. Let's set this animation in motion here. X begins at 0.5 and increases. Notice when x is 1, x cubed is also 1. And now we're seeing x cubed greater than x. And when x is 2, x cubed is 8. And so the area that you see here is precisely the value of g of 2. Now what's the derivative of this function? Now we imagine this integral broken up into two pieces. The first being the integral from some fixed number to x cubed, and the second being minus the integral from that fixed number to x. The derivative of the first term will be 1 over x cubed, that is, we substitute x cubed into the integrand, and then multiply by the derivative of x cubed, which is 3x squared, and then the derivative of the second term would be minus 1 over x, that is, x substituted into the integrand. Since the derivative of x with respect to x is 1, we don't need to worry about the chain rule there. So we have 3x squared over x cubed, which is 3 over x, minus 1 over x, equals 2 over x. Computing the integral. Let f be continuous on the closed interval ab, and let phi of x be the integral from a to x of f of s ds for x between a and b. Now let capital F be any function such that capital F prime of x is equal to little f of x for x between a and b. Since little f is the derivative of capital F, we say that capital F is an antiderivative of little f. Then, since capital F and phi have the same derivative on the interval ab, the derivative of their difference must be 0, and therefore their difference is a constant. In other words, f and phi differ by a constant, so we can say that phi of x minus capital F of x is equal to some constant c. Since phi of a is equal to 0, we can find the constant by evaluating at x equals a. 0 minus f of a is equal to c. So c is equal to minus f of a, and we have phi of x minus capital F of x equal minus capital F of a. Now rearranging slightly, we have phi of x equals capital F of x minus capital F of a. Therefore, we can evaluate at x equal to b and find that phi of b, which is the integral from a to b of f of s ds, is equal to capital F of b minus capital F of a. Another way of writing the preceding result is the integral from a to b of f prime of x dx is equal to f of b minus f of a. This is version 2 of the fundamental theorem of calculus. So the heart of the problem now becomes that of finding capital F of x given its derivative. In other words, the problem of finding an antiderivative of the integrand. This is called antidifferentiation. Let's make a quick remark about notation here. It will be convenient to use this symbol to represent f of b minus f of a. We read this as f evaluated between a and b. So with this notation, the above formula can be written as the integral from a to b of f prime of x dx equals f of x evaluated between a and b. Example. Let's compute the integral from 0 to 1 of the function 3x minus 4x cubed dx and interpret it as a signed area. To do this, we have to come up with a function whose derivative is 3x minus 4x cubed. It should be easy to see that x is the derivative of 1/2 x squared, and so 3x is the derivative of 3/2 x squared. Also, it's easy to see that minus 4x cubed is just the derivative of minus x to the fourth. So, since 3x minus 4x cubed is the derivative of 3/2 x squared minus x to the fourth, it follows that the integral from 0 to 1 of 3x minus 4x cubed dx is equal to 3/2 x squared minus x to the fourth evaluated between 0 and 1, which equals the value of that function at 1, 3/2 minus 1, minus its value at 0, which is 0, and so the value of the integral is 1/2. Here's the graph of the function 3x minus 4x cubed on the interval 0 to 1. The integral of that function from 0 to 1 is the signed area bounded by the curve and the x-axis between 0 and 1. So the signed area here is 1/2. In other words, the area of the green region minus the area of the red region is 1/2. Example. Find the area bounded by the graph of y equals 3x minus 4x cubed between x equals 0 and x equals 1. Here's the graph of the function. This is the same as in the previous example. What we'd like to do here is find the total area rather than the signed area. To do this, we need to calculate the area above the x-axis and the area below the x-axis separately. In order to do that, we need to know where the graph crosses the x-axis. By factoring, we can write y equals x times 3 minus 4x squared, which makes it clear that the x-intercept of interest here is the square root of 3/4. Now let's also recall that 3x minus 4x cubed is the derivative of 3/2 x squared minus x to the fourth. To calculate the area above the x-axis here, we'll integrate this function from 0 to the square root of 3/4. That will be 3/2 x squared minus x to the fourth evaluated from 0 to the square root of 3/4. Now we substitute the square root of 3/4 into this function, and we have 3/2 times 3/4 minus 3/4 squared minus the value at 0, which is 0. This ends up being 9/16. So the area of the green region is 9/16. Now to find the area below the x-axis, we'll integrate from the square root of 3/4 to 1, which tells us to evaluate 3/2 x squared minus x to the fourth between the square root of 3/4 and 1. The value there at 1 is 3/2 minus 1, and then we subtract the value at square root of 3/4, which is just the 9/16 that we already calculated. Doing the arithmetic, we find now that that integral is minus 1/16. That minus 1/16 is the signed area between the square root of 3/4 and 1, and so the area of that region is plus 1/16. So our total area here is equal to 9/16 plus 1/16, which equals 5/8. One more example. Find the area under one arch of the graph of y equals sine x. Here's the graph. We get one arch between 0 and pi. All we need to do here is integrate the function sine x from 0 to pi. Now, since sine x is the derivative of minus cosine x, the integral from 0 to pi of sine x dx is equal to minus cosine x evaluated from 0 to pi. Now, cosine of pi is minus 1, so the value of minus cosine x at pi is plus 1. Cosine of 0 is 1, and so minus cosine of 0 is minus 1. So we subtract minus 1, and we find that the area of our region is exactly 2. Notice that this is a reasonable value for this area because the region lives inside of a rectangle with width pi and height 1. So we'd expect a value here that is somewhat less than pi. Let's finish up here by stating both parts of the fundamental theorem of calculus. First, if f is continuous on an interval containing a, then the derivative with respect to x of the integral from a to x of f of s ds is equal to f of x for all x in that interval. Second, if f is continuous, and if capital F prime of x is equal to little f of x for all x in the interval ab, then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. Coming next, antidifferentiation.